functional decomposition. It's the first presentation toward the design stage. As you might remember, we identified the needs and make problem statements, set our objectives, and then we specify requirements, marketing and engineering requirements. Then we develop some concepts, then evaluate those concepts and find a technical concept. Now, in the next, we use some design approach to initiate our design. So functional composition is a design technique actually, and it's flexible, straightforward to apply. We simply design the system by determining the overall functionality, and then in an iterative manner, we decompose that system into some subsystems with their individual functionalities. So here you can see the learning objectives. You should understand the differences between bottom-up and top-down design approach, know what functional decomposition is, and then how to apply it. Be able to apply functional decomposition to different problem domains, and understand the concept of coupling and cohesion and how they impact each other.
Sizin sınavlar haftaya mı? Sınavlar haftaya.
Okay, bottom-up approach. We are given constituent parts of the system. So we have somehow constraints at the beginning, and we are supposed to develop a working system. So we build models to accomplish some specific tasks, and then integrate those models in order to create a working system. This approach is, of course, more creative, may lead to efficient subsystem use, but it might be complex and not easy to manage. An example would be given a set of gates could be given and or not gates, and you are supposed to build a computer system. So it's quite complex, but it's more creative. Top-down approach. Specification of a system is given, and you are supposed to develop a working system. Then you simply divide the problem into some abstract models, and then you use iteration. You reiterate the vision until the constituent parts are reached. This has a very predictable design cycle, and we can use the labor efficiently, but we need to spend more time in planning. When we compare bottom-up and top-down design approach, top-down design might be preferable, but in practice, it's more effective to work between bottom-up and top-down approach. Okay, functional decomposition. is simply how we implement the top-down approach. It's based on divide and conquer principle. We design a system by determining the overall functionality, and then iteratively we decompose that into subsystems, each with its own functionality. Okay, here the functionality is very similar to what we define in mathematics. So we can make an analogy. On the bottom, you can see a model. We have input X and output Y. So Y is somehow is a transformation of X. Here, this transformation is simply function. If we have multiple inputs here, so X is going to be a vector and Y is going to be a vector as well. So then we can extend this somehow into multiple input, multiple output cases. So here, the model is simply a subsystem or a block in our design, and it performs a specific function. In functional decomposition, then we start with level 0, which is the highest level. We simply define the overall system as a model and determine the inputs and outputs. Next, we have level 1, which is called design architecture, where we usually give some major models or subsystems. Then we continue until level N, where we have detailed design. So at level N, or in detailed design stage, we have no further decomposition. So the system should be ready to realize all components at circuit level should be defined. Once you give this detailed design to an engineer, then he or she can build the system without your help. So in our projects, N will be 2. That's the reasonable number, but it might be 3 or 4 in some cases. So I will suggest to have level 0, 1, and 2, and in level 2, you should give detailed design. So let's see divide and conquer. We split a model into several submodules and then define the input, output, and behavior. When we iterate this until you reach a realizable components, so we stop. So we can show this as a flow chart here. Level 1 comes after level 0, where we define functional requirements. And then the first stage will be design architecture, and we define functional requirements for the first level. And then we compare whether this level 1 gives the detailed design or not. Apparently, level 1 is design architecture, so we go back to the design and then iterate and take N2, and then we repeat this until we achieve or we reach the detailed design, where all components at the circuit level should be defined. Here we have an example. We'll be discussing this in the next several slides. Digital thermometer design. Here you can see the requirements. System must measure temperature between 0 to 200 degrees in Celsius. Should have an accuracy of 0.4% of full scale. To display the temperature digitally, including 1 digit beyond the decimal point. be powered by a standard voltage outlet, so 120 volt in US or 220 volt in Europe and Turkey. Must use an RTD thermal resistive device that has an accuracy of 0.55%, 55 degrees in Celsius over the range, so 0 to 200 degrees Celsius. The resistance of the RTD varies linearly with temperature from 100 ohm to 178 ohm within the range of 0 to 200 degrees in Celsius. So once when the temperature increases, the voltage should increase linearly. Sorry. So here, then we can draw a block showing the level 0 design. We have inputs here. There are two inputs actually. First is the temperature. In the environment, so ambient temperature. Power, we apply to the thermometer, and the output should be a digital temperature display. So that's the lowest, highest level, so simplest design level. So we have to then divide this into models. Divide and conquer principle. Before that, let's see how to define the model. At level 0, the model is digital thermometer, so the thermometer itself. We use a table to describe the model name, inputs, outputs, and functionality. So the model name here is digital thermometer. Inputs are ambient temperature and power with the range given here. And the output should be digital temperature display, 4-digit display, including 1 digit beyond this point. And its function simply displaying temperature on digital readout with an accuracy of 0.4% of full scale. So we start with this design, and then we have design architecture. In order to develop a design architecture, of course, we have to collect information and look into the existing products, and then try to understand which methodologies or design architectures are used there. So we select somehow some of those design architectures and use concept generation or evaluation processes. At the end, we should have a design architecture like this. That's level 1 design. Here you can see 5 models. We have 2 inputs, ambient temperature and power. So this block here actually shows our digital thermometer in previous level 0. The first block is temperature conversion unit. It is simply it's an RTD as it's recommended or defined by the requirement. It converts the temperature into voltage level. So at the output of this block, we have VT and analog voltage. Next, we convert this analog voltage into a digital one. So we use an ADC, and then we use a BCD conversion unit to derive the display, where we need a 7-segment LED driver. So all of this should be somehow powered up. So we need a power supply. So as it's suggested, the VT, the voltage, is proportional to the temperature, ambient temperature, with a coefficient alpha. So once we convert this VT to digital bit stream, we may use an ADC. There are many commercial ADCs. Then we can select one that is suitable to our design. And we got N bit binary output here. BCT, binary coded decimal, simply used to generate four numerical values that should be applied to 7-segment belt display. As you can see, we have 7 numbers here, so each is represented by BCT 0 to 3. So let's see each block then, each module, sorry. The first module is temperature conversion unit. So the inputs are easy here, ambient temperature and power, which are the inputs to the overall model in level 0 design. The output should be VT. That's a voltage, analog voltage, proportional to the temperature with a coefficient alpha. We do not know the range of voltage here. We have to determine. Functionality, it produces an output voltage that's linearly proportional to the temperature, and it must achieve an accuracy of some unknown here. We have to determine this. So that's the thing that we have to work. Analog to digital converter, as we said earlier, usually we commercial ADC, so we do not design from the scratch. We have to, however, determine the most appropriate ADC. As we have VT voltage within a range, then we can determine the number of bits to represent this VT. So that's the design parameter that we have to think about, and highly dependent on the accuracy of the system. Functionality, simply it converts analog input to binary digital output. BCT conversion unit. Model name is BCT conversion unit. Inputs, we have 10-bit binary number here. That represents the range from 0 to 200 degrees Celsius, and the power, as usual. Here we have 4 BCD outputs, BCD 0 to 3. Each is a 4-bit representation of 10th digit, 1st digit, 10th digit, and 100th digit. We simply imagine that 200.0, that's the maximum that we can measure. Functionality converts the 10-bit binary number to BCD representation of temperature and must refresh the display twice a second. So this was not a requirement, but somehow determined in our design. Here, note that the ADC is chosen as a 10-bit one. This could be justified by some calculations. This is very much related to the accuracy that is required by the customer or the designer. So finally, the 7-segment, the one before the final one, 7-segment LED driver. Here we have 4 inputs or 4 digits of display, and the output is a 4 7-segment driver lines. The functionality converts BCD for each digit into outputs that turn on LEDs in 7-segment package to display the temperature. So finally, the power supply, it powers up all components. So its input should be the voltage in the country, standard AC, 120 volt or 220 volt. Output should be some plus and minus DC voltage. This should be determined, and the output current should also be determined. So these are some design parameters, and there should also some regulation target. The functionality convert AC output voltage to positive and negative DC output voltages with enough current to drive all circuit subsystems. Okay, so this was an example of how we use divide and conquer principle. Here we use level 0 and level 1. We can go further, divide any model into submodules in any of the projects. Here, it seems that this is not necessary. Okay, finally, coupling and cohesion. While we are designing a system, we have many modules, as you see from the previous slide. There were 5 modules, and each somehow is connected to some of the others. So coupling is the extent to which modules or subsystems are connected. So somehow that's a measure of interdependence of modules. If we have more exchange of control and data between the modules, we have a higher degree of coupling. So the modules are highly dependent on each other. So the system will be highly coupled. In order to see the number of connections, we can consider number of modules as n. Then the maximum number of connections will be n times n minus 1 divided by 2. So if we have 2 modules, then it's going to be 1 connection. If there's 3 modules, then 3 times 2 divided by 2, so we have 3 connections. If we have 4 modules, then 4 minus 3 times 4 divided by 2, it makes 6, so maximum 6 connections. So the number of connections increases with the number of modules, as you can see. This should somehow give an idea about how the system will be, how much the system will be coupled. Look into the number of maximum connections. On the contrary, cohesion refers to how focused a model is. So modules with the high functional cohesion are the most desirable. We simply maximize cohesion and minimize coupling in our design, which means that we should design models which are focused on some specific task and makes minimal connection with other models. Highly coupled systems, it's quite difficult to change one model without affecting others. There is a failure, then this failure propagates within the system easily within the over the models. On the other end, in highly cohesive systems, we have more isolated models, which do one or a few things very well. Here we see an example. That's an audio amplifier design. So design architecture for audio amplifier, level 1 design. As you can see here, we have 4 models. We have audio input from the microphone, we have a buffer amplifier followed by high gain amplifier and then power output stage. All are powered up by a power supply. So the input of this system, if we imagine level 0 design, are three: audio input, volume control, and power. And the output is going to be audio signal. So here you can see that the buffer amplifier has just one input, which might affect the functionality of this amplifier, and it's connected to high gain amplifier. So as long as this is powered by the power supply, then we can say that the buffer amplifier has low coupling, not much dependent on the other models. So that's somehow more cohesive in comparison with power supply. Because in the power supply, we have three connections. So if there is a failure in power supply, the whole system fails, which means that power supply is a highly coupled model. Okay? So in our design, anyway, we have to consider the dependency of the modules and try to make the system as cohesive as possible. So in our project then, the functional design, we have level 0 design. We have to present a single module block diagram with the inputs, outputs, and functionality. Next, we should have a design architecture or system architecture. This should be somehow based on conceptual design efforts and evaluation of those conceptual designs. We should have a general technical solution. So this system architecture or design architecture should reflect that evaluated technical concept. So in level 1 diagram, we'll have all modules and interconnections. We should describe the theory of the operation and explain how the modules work together to achieve the functional objectives. We should also present functional requirements for each module. Next, we can iterate this and go into the details of the modules if it is necessary, and then repeat the process for each level. As I said earlier, typically in our projects, there may be level 0, 1, and 2 maximum. Typically, level 0 and 1 might work well.